try to teach this section today and maybe give you guys a birthday tomorrow to finish up the chapter 10 packet and try to get all that done. So we just got done doing hypothesis testing for the proportion. So now we are doing the exact same thing for the mean. So kind of how we have been doing, we find probability for one and we do it for the other. Process is very similar. You have to have a null and an alternative hypothesis. And then you have to check your criteria. When we're talking about the mean, do you remember what our criteria was? Either the original population was normal or a sample is bigger than 30. And then we had to, then we have the choice of either doing the classical or the p-value approach. P-value is probably my preferred method. That's just finding our probabilities like we were doing in the last unit. But classical, like we talked about, is basically looking at, with the proportion, we're looking at z values. But remember on our formula sheet, when we are talking about the sample mean, this is our big difference. When, let's see, we did it like with our confidence intervals for the mean, we weren't using z values. We were using the t values. So that will be the difference. We are going to be looking at the t here. So first I just want to practice using that table and finding these critical values a little more. So when we're dealing with the mean, we are looking for the t distribution. So look at your t distribution table. All right, on this you have to have a probability and a degree of freedom. If we have n equals 30, what would be our degree of freedom? 29. Right-tailed test. So what this means is that the area to the right, that's my alpha, is 0.025. You have to find the t that matches it. So if you look on your table, it tells you this table is giving us area to the right. So we are just literally going when our degree of freedom is 29, when our alpha is 0.05, where those things meet, and we get t to be what?
2.04.
Do you do 0.25?
I did 2 zeros instead
Oh.
of 1. Wait, I got 4 5. I got 4 5.
Yeah. I was looking at one and wrote a different one. It's one of those days. We all have them, right? Okay. B. A left-tailed test with n equals 7 and alpha equals 0.01. So if it's left-tailed, we are looking for, that is a horrible normal curve, but pretend it's good. There to the left. So that's my alpha. How many degrees of freedom do we have here? 6. Okay. We need our t. Now the problem is, this gives us area to the right. If we have 0.01 to the left, that means there's 99 to the right. Do we have that as an option on our table? No. So how would you find that t value? It's a negative. Remember, it's all centered around 0. So you look up the 0.01 and 6 degrees of freedom, and that's 3.143, so we would have the negative 3.143. All right. C, this is where we have to be a little more careful. The two-tailed test. Just like when we were doing two-tailed tests by hand with the proportion, things changed a little bit. If I'm looking at two tails, then technically I would have two different t values, wouldn't we? This one would be a negative and this would be a positive, but they should be the same because it's symmetric. Now if my alpha is 0.1, that's saying together with these two tails, it's 10%. So how much is in each one? How many degrees of freedom? So t, we have two different values, plus or minus, and we look up 0.05, 23 degrees of freedom, and that gives us 1.71. So to find these, we have to be able to find our t values first of all. Is everyone okay with getting the t value for the left, right, or two-tailed? So remember, table gives us the left, or sorry, the right, and if you want the left, you just make it a negative. All right, so our hypothesis testing. We have to have simple random sample, which is normal. Normally what we do here, we can't have any outliers. It has to be normally distributed or greater than 30, so that's the main criteria that we'll check. And of course, they all have to be independent. So first step, just like with the p's, we have to have the null and alternative. Because we're talking about the mean, we'll be dealing with mu, not the proportion this time. So it's just changing that parameter. And we'll have to have an alpha level, which is given in the problem. Then we'll find our test statistic. When we're dealing with the mean, it's like finding a z-score, but it's a t value because we're going to use the t distribution. So it's the same idea. It's r value minus the mean of the null divided by our standard deviation. Then we use that, and then we can, if we're using the classical approach, compare t values. If we're using the p-value approach, we compare the probabilities. So let's take a look at this one. I want to test the null hypothesis. Mean is equal to 80. With the alternative, the mean is less than 80. And we have a sample of n equals 22, which is that big enough? No, but I'm telling you it's normally distributed, so that's okay. It's either or, either bigger than 30 or already normal. So part A, compute the test statistic. That's really like a z-score, except we're dealing with the variable t for these things. So if we're going to find it, we need the mean of the null and we need our standard deviation. So we can do that. There's different options. You know, the slide I just had gave you a different formula for the test statistic. It's the same thing. It's just if you compute the standard deviation separately or not. It's on your formula sheet if you need it, so this is not anything new. When, let's see, I was trying to look back. If you look under chapter 8 on your formula sheet, your standard deviation and mean for x bar are given. So our mean is just the mean of the null hypothesis, which is 80. The standard deviation for x bar is our sample standard deviation divided by the square root of n. So my sample standard deviation was 8.5 divided by the square root of 22. And we get 1.8122. So our test statistic is kind of like finding a z-score. It's our value, so the 76.9, minus the mean of the null divided by the standard deviation. And we get a negative 1.7106. Everybody with me so far? Determine the critical value at alpha equals 0.02. Sometimes the critical value is also a t, so if you need to keep them separate, you could call this like a t sub 0, the t that goes with our null hypothesis if you want. For my test statistic, how many degrees of freedom do we have? This one. Are we doing left, right, or two-tail? Left. So what that's saying is this area is 0.02. We need the t that goes with it. So what kind of number will our t be? A negative. So we go to the 0.02, 21 degrees of freedom, and we get negative 2.189. So if we were doing this based off the classical approach, it's saying, all right, if you are in this shaded region, then we would reject. We got the t, the cutoff is the negative 2.189. So anything there, we reject. What was the t for our sample? Okay, so remember this is when t equals 0. So is negative 1.7 in that shaded part? No. So our conclusion, since the t for our sample, or the t sub 0, is not in the shaded region, we fail to reject the null hypothesis. There is not enough evidence to conclude that the mean is less than 80. So that's the classical approach. You find your test statistic, you look for the t for your sample. If it's in the shaded region, you reject. If it's not, you fail to reject. Any questions there? Let's look at another example. Okay, assume the resting metabolic rate, or RMR, of healthy males in complete silence is 5,710 kilojoules per day. Researchers measured the RMR of 45 healthy males who were listening to calm classical music and found their mean RMR to be 5,708.07, standard deviation 992.05. At the alpha equals 0.05 level of significance, is there evidence to conclude that the mean RMR of males listening to calm classical music is different than 5,710 kilojoules per day? So, what do I need to do first? We need to look at our criteria, and we need our null and alternative hypothesis. We're talking about the mean, not a proportion here. What's the difference? If I'm talking about a proportion, what kinds of numbers are we getting? It's either a percent or it's written as a decimal between 0 and 1. This even says somewhere in it, doesn't it? Yeah, we have a mean here, so we know we're talking about that. What's the criteria for mean? Greater than 30 or already normal. I told you that we had 45, so that's bigger than 30, so we're good. The null hypothesis, since we're talking about the mean, we'll use a mu. Null is always equal to something, so my baseline is the mean is equal to what? Alternative. What am I trying to test? I want to know, is it different? So different could be bigger, could be smaller. So we are just looking at not equal to. There. Okay, so we checked our criteria. We know we can proceed. We have a null and an alternative. Since we're talking about means, do we need to find z's or t's? t's. Now, the idea is the same. It's the mean of the null minus our mean divided by our standard deviation. Okay, so we need to know those things. All right, so what is the mean for our sample? If we are looking back, the group we had, what was our mean? We'll call that x bar since it's for the sample. What did it say in the problem? Okay, so our standard deviation, how do we find that? S over the square root of n. So our S was the sample standard deviation, 992.05, divided by the square root of n, which was 45 here. And you get 147.8861. So to find the t that goes with our data, t sub 0. It's our value minus the mean of the null divided by the standard deviation of our sample. We get a negative 0.0131. All right, so different options for how to proceed. If I were trying to do the classical approach, this is our value. We would have to compare it to the sample. How many degrees of freedom do we have? 44. We're testing not equal, so that means we have two n's. So we have two t's here. What was our alpha level? 0.05, so we split that in half and we get 0.025. From the table, t could be a positive or negative. Let's see, so 44 degrees of freedom, do we have that on our table? No. So what's the closest one we have? 40. So if we look at 40 and 0.025, we get 2.021. Hello.
Do you mind if we take a little show?
Okay, so we have our t value. That's our cutoff. So negative 2.021, positive 2.021. Would ours be in that shaded region? No. So what does that mean?
Fail.
Fail to reject.
What? Wait, get your big elbow out of my face. Wait.
Yes.
Oh, the negative 0.0531. The shaded regions are the negative 2.0.
That's the cutoff. So anything smaller than a negative 2.021 and bigger than a positive, you would reject.
And ours was negative 0.0.
Right.
So, wait, so we failed to reject.
Yes.
I can't do this.
downside of that, I'll put it away. We're pretty limited on our t-table, aren't we?
Yeah.
We only have certain percentages. We only have certain degrees of freedom. So most of these we are going to be relying on our calculator to do. So let's talk about how we would do this on our calculator.
I feel like you should lead with on the calculator.
No, because you should know how to do it. And not just rely on your calculator.
I don't
So-
know how to do anything on this calculator.
We are going to go to stat. Tests. All right. So if we look at our options, stat tests, we are going to do number 2, the t-test. And with these, you know if you pick the wrong one because it's going to ask you for information you don't have. All right, so we have options. Data means you have original values that you entered into a list, which we do not have. So we're going to go to stats, and it's going to ask me, mu sub 0, that is the mean of the null hypothesis, which was 5710, the mean of the null. X bar was our sample mean, which was okay, the sample standard deviation. So that's the one, not what we calculated when we did S over N. It's just straight from the problem. It said the standard deviation was in. How many were in our sample?
45.
What were we testing? Not equal. And then if we go to calculate, I'm going to drag this over here so people watching the video know what we did. Okay. So then we get this. So we did stat test 2. So we are testing not equal to. We get a t. Is this the same t that we got by hand? Yes. Now, when you do it on the calculator, it's giving you the actual probability, the p-value. We didn't really do that one. I keep showing you the classical approach because our table for the t-distribution is just not very user-friendly for finding a good probability. So that's why I keep showing you the classical approach. But on the calculator, it's a lot easier to do the p-value. When we look at this, if you were doing it on the calculator, I would ask for you to write down the t and the p that you got. What this means is if your null hypothesis is true, there is a 98.96% chance of getting the sample mean that we found. Is that unusual at all? No, that's a really good probability. So that means our null hypothesis is probably true. How did we decide for sure if we reject or not based on the probability? You only reject if p is less than alpha. So our alpha was what, 0.05?
Yeah.
So obviously p is greater than alpha.
So we filtered.
Mm-hmm.
I still have a headache.
Okay. Let's look at another one. I'm going to do it by hand and on the calculator again, just to show you both options. Do you want me to do the calculator first? Would that make you happy? Okay. Ava wants calculator first this time. According to the United States Mint, quarters weigh 5.67 grams. A researcher is interested in determining whether state quarters have a weight that is different. He randomly selects 18 and gets the following data. All right. First of all, do we have enough to assume it's normal?
Yeah.
We have 18. Is that enough?
No.
No. So I really, I meant to include in this problem that it was normally distributed and I failed. So that's my bad on that one. So let's just assume this is normal because it does not meet the criteria. What is my null hypothesis that I'm testing? mean is equal to 5.67. And then the alternative would be that it is not. Because I said different. Alright, now this one is one that we would probably want to use a calculator for anyway, because did I give you any of the information? No, and you're going to have to go to that calculator to find your sample mean and sample standard deviation anyway. So go to your list and enter all this data.
I do not know what you know already. Okay. Like, there's no way you did already. Yeah, but there is 18. How the heck? I just got fast fingers. What's happening?
Okay. Then where do we go after this? But this time I'm going to base it off my data. So we still have to say the mean of the null, 5.67. The list, you have to tell it where the data is. So L1, make sure those frequencies are set as 1. We are testing not equal. So what I would ask, if you did this on your calculator, please show me something. So tell me what your T was. And our P. What?
I'm just tired.
And then how do we know if we reject or not?
If it's less than alpha.
So is P less than alpha?
So this is when we just reject.
So what that means is there is evidence to suggest the alternative, the mean weight for state quarters. Is different. Let's talk about how to do this on the calculator. Or sorry, by hand. We just did the calculator. By hand, we would still have to use the calculator to get some of our stuff. So we need the mean and standard deviation. Where did we go to get that stuff?
Stat count 1. Is that right?
So make sure list is L1, frequency list is empty. So from that, we would have that the mean is 5.7022. Standard deviation, the S, 0.0497. Now that's for the sample, but when we compute the T statistic, we'll have to do something else there. If you forget, it's probably the easiest, just look at your formula sheet. So we're in chapter 10, and it has on there the T sub 0. So when in doubt, just go back here. It's X bar minus mu of the null divided by S over square root of it. So if you needed to go back there, the X bar, we just got 5.7022. What was the mean of our null hypothesis on this one? Okay, the S we just got from our calculator. divided by the square root of n. How many did we have? And it tells us on our calculator too. 18. So if we did all that,
Wait, what is this finding?
we're finding our t statistics. So I'm just showing you how to do it by hand.
Are you not gonna read that?
It's chilly.
So we get 2.7488. How did that compare to the t our calculator got? Very similar. It is slightly. Did I plug in something wrong? Seems like it shouldn't be off as much as it. Is that what you guys got when you plugged it in? I think it's just due to the rounding of our mean and our standard deviation, so it's slightly different. If we went to 2 decimal places, they would round the same. So then, when we were looking at it, we know we reject if this is in the shaded region, right? We were testing not equal, so that means we would have 2 n's. How many degrees of freedom were there?
17.
Okay, what was our alpha level? So we would have to split that up because we had 2 n's. Okay, so if you go to 17 degrees of freedom and 0.025, that is on there. And that's 2.110. So we'd have the positive and the negative. 2.7488. Where would that be? It would be all the way over here. So is that in the shaded region? Yes. So it's in the shaded, so we would reject. So that's how you would look at it by hand. All right. So just trying to show you guys all the different options. One more. Yes.
Are we gonna always do it on our calculator, or will you have us do it like this one?
I might have you do one of them by hand, and then, but the majority we will do on our calculator, especially because just the T table doesn't have a lot of what we need. All right. So sometimes, if you have a really large sample, the results could be statistically significant, but not have any practical significance. So statistically significant might tell us we reject the null hypothesis, but in practicality, it really wouldn't make a difference. So I just want to show you an example to kind of illustrate what this means. So in 2003, the average age of a mother at the time of her first childbirth was 25.2. To determine if the average age has increased, a random sample of 1,200 mothers is taken and is found to have a sample mean age of 25.5 with a standard deviation of 4.8. Determine whether the mean age has increased. Okay, so first of all, do we meet our criteria? Yes. N is bigger than 30, so we're good. What is the mean of the null?
25.2.
What is my alternative? I want to see if it's increased. All right. Let's just do this one on our calculator. So if we go into stats, tests, number 2. Do we have data or stats this time? Stats. Data is when you have like a whole list of all 1,200 mothers that we're looking at.
Not bad.
So stats. The mean of the null is 25.2. X bar means what? The mean of the sample, which was
25.5.
S is the standard deviation of our sample, which was N. How many did we have in our sample? And what were we testing? So, your calculator should look like this. Then we can calculate it. Right, so on your homework or something, what I would expect right now is for you to write down your T, which is 2.165, and our P, 0.0153. Okay, what was our alpha level?
0.05.
We reject if P is less than alpha. So what do we do here? Yep, P is less than alpha, so we reject the null hypothesis. There is evidence the age has increased. Okay, so we have statistical evidence. Okay, we rejected our null. Practically, let's think about this. If I said the mean was 25.2 years, and now it's 25.5 years, is that really much of a difference? No, you're still 25 years old, it's just a couple months later. So, statistically, yes, the age has increased. Practically, does it really mean anything if you're a few months older? No, not really. So just keep that in mind. Even though you might get a reject, it's not always like an earth-shattering result. You know, sometimes it really isn't much of a difference at all. All right, any questions? So I am done with 10.3. That means you can do the entire chapter 10 packet at this point. Tomorrow is a work day. We don't have school Monday. Tuesday will be a review day. And then we are going to have a chapter 10 quiz next Wednesday. Quiz next Wednesday. Okay, so you have time to work now and you will have all day tomorrow.